Hello everyone, and welcome to the first installation of Henry's problems. The problem we're going to be looking at today is the Gaussian integral, which is a fairly complicated integral at first glance. You have an improper integral from minus infinity to infinity, and then an e to the minus x squared. Minus x squared as an exponent cannot be integrated with normal techniques like integration by parts or u substitution, but there's a few tricks that you can learn to make this integral solvable. So let's get into it. The first thing you want to do is square both sides of the equation, and then rewrite the equation as I squared is equal to two of these integrals, one times the other. Times another integral, e to the minus x squared dx. Now we need to notice something. Whatever x is, or whatever variable represents x, doesn't matter. We'll get the same value for I if we integrate with respect to y, z, anything. So we're going to take this integral and we're going to change the label that we use for the variable. We're going to call it y. And then we're now integrating with respect to y. And then we can combine these two integrals because the functions that we're integrating have an equivalent base, so we can add their exponents and rewrite it as two integrals, both from minus infinity to plus infinity, of e to the minus x squared plus y squared dx dy. So now we have a double integral that's equal to I squared, and if you've taken Calc 3 and seen a lot of double integrals, you might notice that we could make this integral easier by changing coordinates. In this case, changing to polar coordinates, because in polar coordinates x squared plus y squared is equal to r squared. And so changing to polar coordinates, bring it up here, we will have an integral in terms of theta, an integral in terms of r, and our function with our polar values substituted in will be minus r squared times our Jacobian r dr d theta. And since our bounds for our x and y are from negative infinity to positive infinity, to cover the same area, which is the whole 2D plane, we're going to integrate theta from 0 to 2 pi and integrate r from 0 to infinity. And the first integral that we have to do, the one with respect to r, can be easily done with a u substitution. So we will let u equal r squared so that du is equal to 2r dr. And so 1/2 du is equal to r dr. So we substitute in 1/2 du for r dr and u in for r squared. And making that substitution, we are left with the integral from 0 to 2 pi, the integral from 0 to infinity of minus e to the minus u du d theta. And so now we evaluate this integral, and the integral of e to the minus u du is minus e to the minus u du. So we then have minus, forgot the 1/2 proportionality when we made the substitution. So we have minus 1/2 times the integral from 0 to 2 pi. This is just our theta integral, we haven't integrated in that direction yet, of e to the minus u evaluated from 0 to infinity. And u we substitute back in when we evaluate r squared and d theta. And when we evaluate this, e to the minus infinity, when we plug in infinity for r, is a very, very small number. So small that we call it 0. And e to the 0 is 1. So we would have 0 minus 1, but then there's also a minus sign out here. So this would just be 1/2 times the integral from 0 to 2 pi of d theta. And the integral from 0 to 2 pi of d theta is 2 pi. So we have 1/2 times 2 pi, which the 2's cancel. And so our final value for the double integral that's equal to I squared is pi. And to solve for our original thing that we wanted to solve for, which is just I, we just take the square root of both sides. I equals the square root of pi. And that's how you solve the Gaussian integral.